apologize for the math. I really want to try to open more. I'm trying to give you a little bit more of a gateway to things that are out there, right? And I hope that's okay. And again, there's not going to be calculus on our homework, right? They're still doing that. But I am going to ask you to plug in some data into a distribution and give me a height. But there's functions in R to do that, and I'll show you some of those. And I'll give you an example before I ask you to do it. And of course, you know where to find me. You know where to find Jihong. Some of you figure it out and solve it too, and then you submit, and you see all this red, and you say, Templin, what happened? And I say, I know, right? At least the green boxes worked. Sorry. At least I can try to make fun of myself. By the way, you're welcome to make fun of me too. Totally cool. Like, that's how we know, like, we're all on the same footing. If you can, like, poke fun at me, like. That's right. But you can make new and interesting ones too. Come on, Templin. That's a good one. My son now, he's like not even 3 yet. Come on, Dad. Yeah, come on, Dad. All right. Yeah, Hugh. That's great. Good job. Okay, so we're going to get into maximum likelihood, but we're going to do this with our regression now. So how does, this is the problem I always had in stats classes, like the theoretical ones, is you get this, someone talking about a mean, great, yeah, that's fantastic. I know there's a mean out there, but really I've got these betas I need to go and figure out. Right. So the key to linking the two together is, remember where we started with our empty model? We had beta 0 and nothing else. And the estimate of beta 0 was the mean. That's how we start. So sure enough, we are going to go through the same process, putting this in the terms of regression. And NLME and LME4 sort of do this for you. What you end up getting here is the distribution that's assumed. So this is remember our regression model. If we have y equal to this function beta 0 plus beta 1x plus beta 2z plus beta 3xz, just throwing it out there, then the distribution we're going to do that we use for this likelihood function would be normal, and the mean value would be given by our predicted value for each person, right? So we know they're x. We know they're z. We don't know the betas, but we take a guess at all of them. So with our guess for the betas and with everybody's observed x and z, we smush them together and we make a predicted value. And that now becomes the mean for each person. Sure enough, if people have a different x and a different z, if there's variation in that, people are going to have different predicted values, different predicted means for each of those, right? So you can see how that would work. Similarly, we're still predicting the variance. Right? So now, instead of having a likelihood function that we could show with 3 dimensions, like where we had a mean on one side, a variance on the other, and the height, with this one linear regression model, now we have 1, 2, 3, 4, 5 different parameters we have to search over. So that would be a 6-dimensional shape that we have to show. Right? So this is why, for me, why this stuff doesn't fly well once you get after the simple examples. But the process still maintains the same. We take a guess for the betas. We take a guess for the sigma at the same time, or sigma squared at the same time. We plug that into this function, and it tells us the height. And we go along. Turns out, though, it's kind of neat. In the mixed models, and the stuff that really does most of the stuff, the models that we're going to get into when we get into multivariate, these models actually rely upon what we're doing in least squares a little bit. In that, for every sigma squared that you guess, it implies a solution for the betas. So it will guess sigma squared for you, and then it will do least squares to find the betas. So the process will be, I don't need you to guess the betas. I actually know them. For every version that you give me with sigma squared, I can figure out what the most likely betas would be that go along with that. So all I have to do is guess over sigma squared. But it uses this process, and what I want to do with this is show you how we use iterations to figure out the guess and check of maximum likelihood, right? What I had done previous to this was what's called a grid search. The most naive of searches for a parameter there ever is, because it's really labor intensive. I have to try every possible permutation of numbers over a wide range to figure out where the peak of a function might be. What LME and what Elmer and NLME do is, maybe we'll just call this Nelmer. Nelmer and Elmer? Can we do that? Does that sound good? What these programs do is use a process that's called Newton-Raphson. Anybody heard that before? Newton-Raphson is a way where we use a little bit of calculus to go make an educated guess as to where the peak of the distribution should be. Right? So we start off with a naive guess. What you're going to see in logistic regression when we go with the next online lecture that I was showing you today, the algorithm that we're using guesses that all the betas are equal to 0 to begin with. Always. Every beginning guess is that. That's pretty naive, right? Betas, all 0. All of them. Wouldn't that make life easier? There's no effect. It's all random, right? It's there's sort of like chaos theory behind that, right? Something like that, right? I don't know. Anyway, but regardless of where the nice thing about Newton-Raphson is, regardless of how naive our guess happens to be as to the parameters to start with, this process will sort of ensure that eventually, if we run the algorithm long enough, this guess and check algorithm, that we'll find the maximum of a distribution that has a single maximum, which is pretty cool. It's basically a hill climbing algorithm. You drop someone in on a hill, it figures out the direction to go in that gives you the steepest ascent, and then once it starts to level off, right, and you say, I took a step, but I didn't change in height, that's essentially where that tangent line would have a flat slope. That's the maximum. So it goes much faster than this. So for instance, this is how it works. We use calculus. I'm not going to go too far into this, but let's imagine we started way over here. We take a step, and we take another step, and we see the difference between the two steps is small. We end up stopping. So these algorithms that we talk about with maximum likelihood, when we don't have a closed form in that room, we don't have just an equation to give us the numbers, we have to come up with some rule to say, yeah, that's close enough. My last step and the height of my last step and the height of where I'm at in my current step are so close together that I'm effectively on a flat line at the peak, right? That tangent line of the curve. What this is called in algorithms is the convergence criteria. Have you seen that before in any statistics? Maybe you haven't. You're going to see that almost from now on. And here's the thing. There are multiple ways of saying, yeah, I'm close enough to the peak out there. But it's all through convergence criteria. If it meets the criteria, if your height, the relative difference or the distance between the two heights at two different steps is virtually 0, it's like saying the slope is 0, so it stops. The question is, what level is close enough to 0 to say that's good enough? So that's the process. How it works is this version through Newton-Raphson. Basically, we take our old guess at a parameter, we take some combination of derivatives of the likelihood function, I'll just say that, and it gives us a new guess, right? So over here might have been an old guess, here's a new guess, and sure enough, it's going uphill. And so we're going in the right direction, hooray. So here's an example with our data. It's with 5 observations. And sure enough, this NLME algorithm works very similarly to the LM function that we saw before. So we just tell it a model. Here I'm telling it IQ tilde 1, which means I just want the empty model to be estimated. We use method equals ML. It starts to search, and sure enough, it gives us a log likelihood. It gives us an estimated mean of 114.4. Standard error of the mean, which we could have found ourselves. It also gives us a log likelihood of negative 10.7. And wasn't that pretty close to what I had found on that slide before? It was pretty close to that. Uh-oh. I just did something bad. Hang on here. It's coming back. I can do this. There we go. My bad. So the only difference between this and the LM function is the inclusion of method equal ML as an argument. But the steps it's doing, we can actually see that it had convergence. Here it goes. Whoops, not quite. Gives you some of the objects, gives you some of the names, and it should tell you that you have convergence. It tells you the residual standard error, which is, again, that's the square root of sigma squared that we had found before of 2.05. And if I just, here's a bad idea, but if I took, what was my estimate for it? It was, what was my estimate of the variance? 4.992, thank you. If I take the square root of 4.992, I should say that this is not quite the same. Oh. Sorry, 4.24? Well, I could find it, but let's just imagine. Let's just go with this. That's the square root of what we found. Within rounding error, right? Square roots and squares are a little tough. There's a lot of rounding error in a square root function. So, log likelihood's pretty spot on. I do remember that number, negative 10.7. So we're pretty cool with that, right? So the process I'm telling you is it's searching and it found what we had found before. And it gives us these fixed effects here for the value. This t value comes from beta 0 over the standard error of beta 0. That, again, is a Wald test. But when we do ANOVA, our ANOVA table for this does not give us a mean square error. It does not give us a full ANOVA table anymore. It's gone. And that's why I don't like the ANOVA table. That's why I don't even remember what's in them anymore. I don't ever use them anymore. And that's because our tabulation of error and tabulation of things don't come directly from the method. We're searching for, effectively, the mean square error. Mean square error of that table, right, which was sum of squares error divided by degrees of freedom error. That thing is what we're looking for with this algorithm now. And we get that through the search process rather than through the formulas that we used to use. Questions? I'm losing it here. Let's talk about some useful properties, shall we? Yes, thank you. I like that. We can do likelihood ratio tests. Sometimes these are called deviance tests. That makes me laugh at it. Oh, yeah. This model's deviant. Wald tests, information criteria. So now we're going to go past our simple model and we're going to consider a model where we try to predict IQ from job performance, right? Pardon me, predict job performance. This is Y. Job performance is Y. IQ is X. But we're going to mean center IQ at 114.4. Why? Because I dig centering. I should give out hats that say that. I center. No. Maybe not. I'm trying to think here. There's dance examples, right? Find the center, right? No, I don't know. Never mind. So the empty model was Y is predicted by beta 0. That's saying our best guess for everybody is just the mean. Our new model will have some type of prediction function where there's a slope for every 1 unit increase in IQ. The mean job performance will change by beta 1, right? Okay, so we plug that in our GLS syntax right up here. This is our empty model. Right? And here is our model where we predict performance with IQ. Can everybody see that? There we go. There we go. So empty model. Because we didn't use performance before, it's now the dependent variable. It's on the left-hand side of the tilde. And a 1 over here gives us the intercept. And for IQ, this is the part of the code where I mean center it. And then right here, you put it on the right-hand side of the tilde saying it's our value we're predicting. Is that better? Okay. So first question I'd like to ask is, how do we test the hypothesis that IQ predicts performance? There's 2 ways. We fit 2 models. We fit this model right here, the empty model. We fit a model with a predictor. And you'll note beta 1, if beta 1 were to be equal to 0, the model with the predictor would be equivalent to the empty model. You see that? So that means the empty model is nested within the model and with the predictor. So that's a key term in likelihood ratio tests and in maximum likelihood, the idea of a nested model. A nested model, or for a pair of models, for one of them to be nested in the other, means that you have to do something, put some type of constraint on the model with more parameters, that if that were true, you'd end up with the model with fewer parameters, right? So case in point, our model with the predictor has one more parameter. It has beta 1. But if I put the constraint that beta 1 equals 0 on that model, I would end up right over here at our empty model where we were before. Right? So if we can put some type of constraint on our parameters in the model that has more of them, we end up with a nested model if it's equivalent to the model that has fewer. And the way I want you to think about these is the model with fewer parameters is something we're going to call the null model. You see where I'm going with this? And the model with more parameters, anybody want to guess what we're going to call that? The alternative model, that's right. And so now it's effectively the case where we're going to set up a hypothesis test. Can you guess what the hypothesis is? The null hypothesis is effectively like the null model is true, pardon me. Or more specifically, that beta 1 equals 0. It's the constraint we had to put on the alternative model to end up at the null model. The alternative model would be that, this is a 1 here, beta 1 is not equal to 0. There's two choices, right? It either is 0 or it's not. If beta 1 were to be 0, this alternative would show up like the null. Right? But if beta 1 was not 0, then the alternative would have to be needed to describe the data more than the null. Does that logic seem to go pretty well with you? So that's literally how we're going to do our model comparisons in maximum likelihood. We're going to form, particularly in linear models, we often form a series of these nested models. We start with maybe an empty model. We add in some type of predictors. We add in some more predictors. We take out some predictors, right? There's these series of things where we're adding or subtracting, but we're adding them to a model in the previous step. Right? Whenever we add predictors in, we have a new alternative model. Right? Excuse me. All this Mardi Gras partying has got my voice starting to crack here. So, likelihood ratio tests are used there. Right? So we're going to compare the log likelihoods of these two models when we have nested effects. Alternatively, we could just look at the Wald test, right? What was the Wald test again? Parameter divided by standard error. Well, in the Wald test, if you think about it, all we need to do to test this hypothesis, we don't need to go and estimate two models. We just need to estimate the alternative model down here, this one. If we estimate the alternative model, we can do a Wald test for beta 1, right? And so this is sort of what happens in maximum likelihood. We have these in nested models. We'll have a smaller model. We'll have a fuller model. We'll have the null model, the alternative model. Wald tests work on the alternative. Likelihood ratios compare null and alternative. Can you imagine if there'd be a test that worked on the null only? Like, hey, we should have added that effect. Sure enough, there is one. It's called a score test. I won't talk about it anymore in class. Bless you. But in likelihood theory, they have all three combinations. The score test is really cool because it's like, should I have added that predictor? Oh yeah, I should have. But you didn't even add it in the first place. It's like voodoo. It's like clairvoyant. But it's kind of cool too. Anyway, so what we're going to do is start with likelihood ratio tests. A likelihood ratio test, again, sometimes called a deviance test. More often in categorical data, it's called a deviance test. We take the likelihood value, a comparison of the likelihoods, or the log likelihoods, from a null model and alternative model. So to use a likelihood ratio test, the models must be nested. Right? If they're not nested, we have another thing coming to talk about that. But if they're nested, again, the definition of nested is the model with more parameters. If you apply a set of constraints to that, you end up with the model with fewer. Right? The alternative model plus constraints leads you to null. Right? For our purposes in class, most of our models are going to be nested. And most of the things you do in the ANOVA regression type, linear model type, even if you change the distribution, are going to end up being nested models. So likelihood ratio tests show up a lot. What it happens to be is, this is a delta, the change in -2 times the log likelihood. Or let's put it a different way. If you use maximum likelihood for both of these models, you estimated the null, you estimated the alternative, you get the log likelihood for the null, get the log likelihood for the alternative, take -2 times the difference in those, and you end up with a test statistic. This thing follows a chi-square distribution, always in ML. Well, assuming the regularity conditions were met. It's chi-square. The degrees of freedom of this chi-square is equal to the difference in the number of parameters between the two models. Right? So in our example, the alternative had sigma squared, beta 0, and beta 1 we're estimating. And the null had sigma squared and beta 0. There's a difference of 1 parameter, so it'd have a 1 degree of freedom test for it. Well, sure enough, by the way, you don't have to go calculate this yourself, particularly in R. In M+ and SAS, sometimes you have to. But in R, they make it really easy because it saves everything as an object. There's a function that compares the objects and does this for you. And that's where the numbers come from. So here's our example. Our null model is the model where beta 1 is equal to 0. Our alternative is the model where beta 1 is estimated. Right? There's our difference in parameters. There's 1 degree of freedom. It's like I wrote these slides. Foreshadowing here. So the step 1 is to estimate our null model. Here's our log likelihood. Step 2, estimate our alternative model. Here's our log likelihood. I did the math. The difference is -14.4. There is a function in R to give you the chi-square. There's the p-value for it. And sure enough, that p-value is very small, 0.0001. So we would conclude that our null hypothesis is rejected. When we reject our null hypothesis, we're saying that the null model can't be true, or that beta 1 cannot be equal to 0. So I did it the long way here, but sure enough, you remember the ANOVA function that gave you the ANOVA table in LM last time? It still has value even if it doesn't give you an ANOVA table, because using MLE, usually the package creator creates a version of ANOVA that does a likelihood ratio test for you. Let me just applaud R for that, sorry. You don't know how many years of having to do this in like Excel I've had to do like up before now, not now, whenever I switched over to R. So basically I put in the null model, I put in the alternative model, it lists them side by side. Here's likelihood ratio test, the number I just found. All right. The test is 1 versus 2. It doesn't even tell me the degrees of freedom, but I can figure out the difference here. And it tells me the p-value. And we say, hey, thanks, R. So typically when we build models, we have this cascading sequence, right? We start with a null type of model, we add to it an alternative model, we compare the two. And in this example, this alternative model and the null model is when we could have tested using a Wald test. We could have just fit the alternative and tested the beta coefficient. But think of the case where you have like a categorical variable that you've coded, and there's 2 different categorical coded variables you put in your analysis. Right? What's the omnibus test? You can't get that from a Wald test directly because that's beta over standard error. This is how you'd get it. Right? The model comparison would be the way to do it. One way to do it. There are Wald tests to do it. Yes, Ryan.
Start backtracking a little bit. For the log likelihood, is that just the log of the height?
That's it. That's exactly it.
Okay. So it's comparing the heights between one
That's right. The relative heights between the two. Yeah. Mm-hmm.
Since H1 is the only difference, it's looking at the height of H1.
That's right. Yeah. You're welcome. Thanks for asking. Any other questions? So, long story short, this process is going to continue. Whether we're here with the linear model, like regression that we're just doing right now, or pick your favorite, most complicated model we'll have in this class estimated by maximum likelihood. I don't know what that'd be, a multivariate Bernoulli with a Cauchy something or other and a different length function. But we estimate with ML, and here's a null and alternative model, they're nested. Oh, I just put it in an ANOVA, get a likelihood ratio test out of it. Same process, right? So that's cool. So this is going to continue. This is going to be much more general than that ANOVA table that you had before, which is the irony of it being in the ANOVA function. I think that's funny to me. Wald tests are what we call typically 1 degree of freedom tests. You'll note that the difference in these two models is 1 degree of freedom. 3 minus 2 equals 1, right? That's the difference in parameters. We could have, again, tested that by taking our parameter value. If we subtracted it off 0, this is the value of the parameter under the null hypothesis. That's what this theta 0 represents. And compare this with a normal distribution. You'll note in our output over here, it gives us a t-value, and that's because for some distributions we can actually go a little bit further. If you remember in basic statistics the difference between z and t, you vaguely remember that? Like the z-test, we assumed we knew the variance, whereas t, it was sampled, right? In the case where we have the information to form the t, particularly meaning we know the analytics, again, the calculus behind it, we do the t-test. It says t. But more often than not, in many software packages and in many packages in R, this is a z instead. So it's functionally works the same. We use it the same way, even though we know there's a difference between z and t, right? So basically what we could do is, here's our slope right here for beta 1. The slope of 0.96 divided by 0.13 gives us a t-value of 7.09 with 1 degree of freedom. And that gives us a p-value of 0.0058, which again, we'd conclude the same thing. Beta 1 is not equal to 0. We'd reject that null hypothesis. So in the case where we have just one beta to compare, we could just fit the alternative model and be done with it. It'd be fine. The cool thing is, again, maximum likelihood and frequentist statistics all have this, share this thing, where we always talk about in the limit, as n gets really big, the Wald test and the likelihood ratio test give you the same answer. And most of the time in your data, it will give you the same answer too. But certainly as they're asymptotically equivalent, is what we'd say. Well, it's a mouthful. The other thing you could talk about, I mentioned the score test, where you fit the alternative model, but then you're like, oh yeah, I forgot to include IQ, should I have? It would also tell you the same information. And similarly, we could calculate an R-square, talk about the difference in R-square as well, and mention all this as well. So that's for nested models. What about if your models aren't nested? In this case, not nested models mean different sets of, you can't take one set of parameters and convert them into the other through constraints, right? So for the example in regression, that's usually you have one predictor in this model, but you have a different predictor in this model. But what still maintains it's the same people and the same dependent variable. That still has to be the same. In that case, you can't use the likelihood ratio test. Instead, what you do is you compare these information criteria. And information criteria usually end with some type of IC. There is the AIC, which stands for Akeike's information criterion. Right? So basically, if you just focus on this column right here, if these models weren't nested, the way you'd pick a model, the one that you'd prefer, is the model with the smaller value. So here again, we would prefer the alternative model, the model with beta 1 in it. What the AIC is doing is it's taking the sort of the result of the model, the log likelihood of the model, and weighting it by the model complexity. how many parameters happen. So it's basically penalizing how well the model fits likelihood-wise based on how many parameters show up in the model. Right? It's trying to balance parsimony versus need for extra parameters and so forth. BIC is the Bayesian information criteria. By the way, I love Bayes. Don't get me wrong. That's the other tattoo I have. I love Bayes. And it is also sometimes called Schwarz's criterion after somebody who created it. And it works the same way. You look at the column for BIC, you pick the model with the smallest BIC. So in this output alone, you've seen AIC, you've seen BIC. Which one do you choose? Oh, right. Yeah, that's the problem with information criteria. Your advisor said BIC, and you submitted it to a journal. And reviewer 3 comes back and says, hey, you really should use AIC. Yeah, right? So thankfully, in this case, both AIC and BIC agree. But sure enough, wouldn't you know it, there are cases out there where AIC tells you one model is preferred and BIC tells you there's another one. Oh, not to mention there's like 1,000 other versions of these. Right? So if you're getting my picture on it, you're telling me, what I'm trying to tell you is try to stay away from these unless you absolutely have to use them. Because in the case of likelihood ratio tests, if you can form nested models to do what you want to work, you don't have to use these. In fact, don't use those because the likelihood ratio tests, there's this resultant statistics, theoretical resistance, saying that they're uniformly most powerful, which means across any of the types of circumstances out there, across any type of model comparison for nested models, these are going to be more powerful to detect a difference than anything else out there. Now, again, if you meet the assumptions of whatever and so forth. So, long story short, find elegant ways of making nested models to do the tests that you need to do for your research, for your study, and use those likelihood ratio tests. And then you can avoid BIC and AIC altogether. Questions? Have I lost you? Complicated? This is throwing in nuance. Again, the bigger picture is maximum likelihood exists. It depends on distributions. And the way that statistics work is that you pick a distribution, you find a maximum likelihood function in R, it spits out a log likelihood, and this is the process of comparing models and doing hypothesis tests. We look at the beta weights, like we did before for single degree of freedom tests, where we form this model comparison, this likelihood ratio test for anything else from there. And this process stays the same whether our distribution is normal, whether it's binomial, whether it's Bernoulli, whether it's whatever. This process stays the same whether we have one outcome or Ahmed. When you were in structural equation modeling last year, we did likelihood ratio tests from day one in CFA because our CFA model, whenever we do a factor analysis, is actually fitting an alternative model to our null model. Building it in there. So you get to a complicated model right away. You don't know what it is, but you can tell how to model compare it, right? So you got that part? Big picture-wise? Cool. So as you might have seen here, though, maximum likelihood and least squares do differ in their estimates of variance. And for a linear model, that happens to be the residual variance, sigma squared error. Right? So for least squares, we found this residual variance to be 0.39, and for ML, we found it to be 0.234. ML is biased when it comes to variances. Bother you? Yeah. Yeah, Ahmed.
Is that why we use MLR with CFA and IR?
Actually, no. The MLR, which is called robust maximum likelihood in that case, helps with distributions that have too heavy or too thin tails. So we talk about it as the kurtosis of a distribution. The normal distribution says they all should be a certain thickness to the tail, and not everything follows that. No, we actually should be using a different, I feel like we should be using a different estimator in CFA. And there is an estimator that exists to do this. That's residual maximum likelihood, or REML. And we'll end up getting to that part very soon. I'm going to introduce to you the ML version first when we get to the multivariate portion of the course. And that's because to do the analysis, we'll use a package in R called Lavon that we use in structural equation modeling that does this nice multivariate models, but they do it in a way that is very similar to what we're doing already with our LM statement, right? Dependent variable, tilde, and a bunch of predictors. Well, if you have more than one dependent variable, it's going to look very similar to that. So I want to introduce you to that because it's a very direct way of estimating multiple regression slopes or regression functions all at once, but it uses ML. It's a problem because our variance estimates are going to be a little bit biased. So then I'm going to show you how to do that same thing in Elmer. That gives us the option to use REML. Lavon doesn't do REML. Basically, none of the structural equation packages do. And I'll show you how to do that in Elmer, and it's a lot more complicated. So my goal in showing you the ML version first is it's much more direct at seeing beta and understanding what it is, whereas when you get to the mixed model package, you have to code it in a way that has a bunch of extra interactions in present. Right? So yeah, there's a method to all this madness, right? By the end of class, you will be pros at interactions and be pros at maximum likelihood. So, how are we doing? Cool. There's another issue that shows up that I probably shouldn't talk about, but I will. If you're using REML, this whole likelihood ratio test I just did, you can't actually do. Not for comparing fixed effects. You can use it to compare models with different random effects with the same fixed effects. So there's added complications. So that's why I still have a job. I think Lisa, my wife, always says, it's job security. Why is it so complicated? It's job security. So at some point, I'd like to simplify for it all for you, but it is complicated stuff. And I hope today helps us. Questions on all this? We're okay with the big picture? Going to be okay, increasingly okay with maximum likelihood? Maybe? Yeah? All right. Let's finish this up then. Maximum likelihood is sort of the topic today. We're going to take this and run with it next because we're going to create generalized linear models whenever we don't have outcomes that fit with what we assume in our regression in ANOVA. And that's almost immediately for pretty much any research study you're doing. Whether that be dependency in your data, extra correlation, non-independent observations, or whether that is outcomes that aren't normal, there's both of those. But maximum likelihood, or the building of likelihood functions, still plays with us there. And furthermore, when we get to Bayes, the core of Bayes is still the likelihood function, although they don't call it that. But that's the core, right? So it still shows up there. So knowing it now will help you when we get there too. Okay? All right, that's it for me today. Thank you for your time. I will be in touch with you over email about homework issues of weirdness and scoring, about the next lecture. I'll just be on email a lot. And remember my gift to you next week. We have no class, and you got an extra 9 points that I'll add to your grades eventually in Blackboard pretty soon, actually. So thanks, everybody.